the purpose of this experiment is the colorimetric determination of an equilibrium constant. The reaction that we are interested in studying is a reaction between iron 3 and thiocyanate to form this iron thiocyanate complex ion. So what's the definition of an equilibrium reaction? You might not have got to this in the lecture yet. An equilibrium reaction is one that does not go to completion. In other words, once the reaction is gone as far as it's going to, you still have a mixture of products and reactants. At equilibrium, you have a mixture of iron 3 ion, thiocyanate ion, and the iron thiocyanate complex. So your equilibrium is a mixture of all three species. Your equilibrium constant is the product of the concentrations of the products divided by the product of the concentrations of the reactants. Products over reactants. So something you may not yet be used to, you may not have seen this before, is whenever you see something in brackets like this, that means concentration. Usually that's going to mean molarity. That's moles of solute per liter of solution. So a reaction that is not at equilibrium will shift either forwards or backwards until it is again at equilibrium. Alright? So Le Chatelier's principle says if stressed, a system that is in equilibrium will react in such a way as to remove the stress. It's going to seek to undo what we did. So let's say this reaction is at equilibrium. Now we go in and we add iron 3 ion, or we add thiocyanate ion. The system is no longer at equilibrium. It's going to seek to undo what we did. These are too big. So how does it fix this? By shifting to the right, because shifting to the right makes these go down. So this goes up and these go down until this ratio becomes again equal to the equilibrium constant. So adding a reactant like iron 3 or thiocyanate will shift the reaction to the right, whereas removing a reactant would shift it the other way to the left. So note that initially our reaction mixture only contains iron 3 and thiocyanate. When we start out, we're mixing together solutions of iron 3 and thiocyanate. There is no iron thiocyanate complex ion when we start out. So this is formed at the expense of these two. This goes up some, this goes up, and these two go down until it reaches its equilibrium. So initially there's only iron 3 and thiocyanate, so it is not at equilibrium. So the reaction will shift to the right, meaning that as this is produced, the iron 3 and the thiocyanate will both go down. So what we're at here is what we're after is to figure out the equilibrium constant. If we could just figure out what this is, we're going to let it come to equilibrium, mix the solutions together, let it come to equilibrium. Now, if we could just figure out what this is, if we had a way to do that, we could subtract this from the moles of iron 3 and moles of thiocyanate. So how many moles of iron 3 would we have at equilibrium? Whatever initial moles we started with minus the moles of the complex ion. Same thing for thiocyanate. Initial moles minus the moles of the complex ion. So how can we do this? How are we going to figure out this concentration? By measuring the absorbance of the solution. Essentially what we're doing is we're measuring how much light is absorbed by the solution. See, this is a colored compound. It's blood red in color. Any compound that's colored is absorbing light, right? So the absorbance is a measure of how much light is absorbed by a solution, and this is directly related to solution concentration according to the Beer-Lambert law, okay, where A is the absorbance, L is the path length. That's basically the length of solution that the length of solution that your light has to pass through. In this case, that's the diameter of the tube we're using, which is 1 centimeter. And you have the absorptivity, which to make all the units cancel out is liters per mole centimeter. So this is a measure of how strongly the solution absorbs. So in week 1, we're going to generate a calibration curve. That's basically a graph of absorbance versus concentration, which should be a straight line because absorbance is directly related to concentration. And then in week 2, we're going to determine the equilibrium constant. We'll use the graph to determine the equilibrium constant. So what are we going to do with the procedure for week 1? We are going to make 6 different solutions. All right, we're going to mix together solutions of 0.20 molar ferric nitrate and 0.00200 molar sodium thiocyanate. So we're going to mix 10 mils of the iron 3, that's the same, and we're going to mix varying concentrations of the sodium thiocyanate, and then we're going to dilute each flask down with 10th molar nitric acid to a final volume of 50 mils. We're going to use a special type of flask called a volumetric flask. A volumetric flask measures 1 volume and 1 volume only. There's no graduations here. This can only measure 1 volume, the volume it's designed to measure, which is 50 mils. So when you fill it up to the mark on the neck, which you can barely see here, you will have 50 mils much more accurately than could be measured with a grad cylinder, and certainly more accurately than a beaker. You're going to have to mix each solution. What I suggest that you do is take one of those disposable pipettes, suck some of the solution up and squirt it back in several times to mix the solution. Just be sure you have a separate pipette for each flask so you don't wind up cross-contaminating your solutions. Now, the solutions should become progressively darker in color. Why is that? Because we're putting in more and more and more of the sodium thiocyanate solution. Now, note that the concentration of the ferric nitrate is 100 times that of the sodium thiocyanate, right? This is 0.2, this is 0.002 molar. That's 100 times difference. There's a reason why we're doing that. For Chatelier's principle, it drives the reaction to the right. We're also assuming by making the iron concentration so much bigger, we're also assuming that however many moles or your concentration of your complex ion is the same as the initial moles of thiocyanate. In other words, by making the iron concentration so big, there will be very little of this in solution. The thiocyanate will be almost exclusively used to make the iron thiocyanate complex. So we're going to calculate the concentration of iron thiocyanate in each flask. So how do we figure out how many moles of thiocyanate we're starting with? It's the volume times the concentration, right? We're putting in a different amount each time. Just be aware you're going to have to do a unit conversion, right? Because big M, that's molarity, that's moles of solute per liter of solution, right? This will be milliliters, this is liters, so you'll have to do a unit conversion. Then we divide by, we're diluting it down to 50 mils in the end, which is 0.05 liters, so we're going to divide by volume. That'll turn it back into a concentration, dividing by 0.05. So let's do a sample calculation. What is the concentration of the iron thiocyanate in the complex in tube number 2. Well, in tube number 2, we're putting in 1 ml of the sodium thiocyanate solution. Divide by 1,000 to convert that into liters. That's 0.001 liters. So we multiply that by the concentration, which is 0.002 moles per liter, and look at your units. A volume times a concentration gives you number of moles. In other words, liters times moles per liter. The liters will cancel, and that gives you moles. So 0.01 liters times 0.002 moles per liter is 2 times 10 to the minus 6 moles. Then we take the 50 mils, right? We're diluting each flask to the 50 mils total. 50 mils is 0.05 liters. So 2 times 10 to the minus 6 moles divided by 0.05 liters is 4 times 10 to the minus 5th moles per liter. That's the calculation for the second tube. So you're going to set the spectrometer for 447 nanometers. You're going to use the nanometers up and nanometers down buttons, and you will 0 with the first tube. Okay, so what this means is you're going to fill the cuvette with the first solution. You're going to 0 the instrument. That means you press the 0 absorbance 100% T button. We're telling the instrument that this is 0, because the first tube contains no thiocyanate. The first tube contains no thiocyanate. If you go back and look, there was no thiocyanate in the first tube. So you cannot form any of the iron thiocyanate compound, which, like I say, we're telling the spectrometer that is 0. We'll measure the absorbance, then you measure the solution, measure the absorbance of the remaining solutions at 447 nanometers. Be sure you rinse the cuvette with each solution before measuring, all right? And be sure you're recording absorbance and not percent transmittance, although you can calculate one from the other. The absorbance should be a number between 0 and 1. And after you measure the absorbance of all 6 tubes, you'll make your graph of absorbance versus concentration. So what are we going to do in week 2? Something somewhat similar, except this time this time we're actually going to determine the equilibrium constant, right? So note that these two are now the same concentration. This one is no longer 100 times bigger. So again, the concentration of iron is going to stay the same, 5 mils in each flask. The concentration of sodium thiocyanate, or the volume, will go from 0 to 5 mils. And we're going to top each one off with 10th molar nitric acid, 543210. Note that the total volume is the same in each case. Each one is ultimately being diluted to 10 mils. 5, 0, and 5 add to 10. 5, 1, and 4 add to 10. 5, 2, and 3 add to 10. 5, 3, and 2, and so forth. In each case, the total volume is 10 mils. So you're going to obtain roughly 35 mils of ferric nitrate and 20 mils of sodium thiocyanate. Take back to your bench just so you don't have to keep going back to the hood, and do not take more than you need. You're going to use a 10 mil grad cylinder to mix the solutions, but we don't have enough grad cylinders for every group to have 6, so you'll have to use the same one. Just be sure you wash it out each time after you mix the solution. So again, we're going to set the instrument for 447 nanometers, 0 using the first solution, because first solution contains no iron thiocyanate, right? Because we're not putting any sodium thiocyanate into the first tube, right? So you can't form any of the iron thiocyanate complex if you don't put any thiocyanate in. One more time, you zero with this tube. You're telling the instrument that this is 0. And then you go through and measure the absorbance of the remaining tubes. So initially, what is our concentration? We need to figure out the initial concentration. We need to figure out the initial concentration of both ions. So we're going to take 5 mils, that's the volume times the concentration, okay, divided by the new volume, which is 10 mils. This will give you the initial concentration of iron 3. We do the same thing for the thiocyanate, except this is variable from 0 to 5, okay. And then, like I said, you'll go in and measure the absorbance of each tube. You'll use the calibration curve to determine the equilibrium concentration. In other words, that's the curve that you generated last week. So the curve that you made last week, going to measure the absorbance of the tube this week. Then you're going to consult your curve and say, all right, if you have this absorbance, what's the concentration? Right, so use the curve from one more time. Use the calibration curve from last week. You're going to measure the absorbance of the tubes here, and you're going to use the curve to figure out the iron thiocyanate concentration. Right. Well, once we figure out how much of this we have at equilibrium, we can subtract it from our initial concentrations of iron and thiocyanate. So the equilibrium iron concentration is the initial iron concentration minus the equilibrium concentration of the complex. Same thing for thiocyanate, initial minus the concentration of the complex, and then we calculate the equilibrium constant as products over the reactants. So let's do a sample calculation, show you how this works out. Let's do it for tube number 2. So we put in 5 mils of our ferric nitrate. 5 mils times 0.002 molar divided by the new volume, which is 10 mils, comes out to be 0.001 molar. Okay. Sodium thiocyanate, we're putting in 1 mil. 1 mil times 0.02 divided by 10 is 0.0002 molar. Now let's suppose we go in, this is from an actual experiment that we did. Suppose the absorbance comes out to be 0.125. You measure the absorbance, it's 1.25. You consult the graph from last week and you find out that if the absorbance is 0.125, the concentration of the iron thiocyanate is 4.25 times 10 to the minus 5th molar. Right? So we then go and subtract this from our initial concentrations. So 0.001 minus, that should be a minus 4.25 to the minus 5th is 9.57 times 10 to the minus 4th. 0.0002 minus 4.25 to the minus 5th is 1.57 to the minus 4th. Now we can plug all these numbers in, right? So this number divided by the product of these two numbers. So this number divided by this number divided by this number comes out to be 283. All right. Very often, this is summarized into an ICE table, which basically stands for initial change, and equilibrium. In other words, what were the initial concentrations, how much did they change, and what was the equilibrium. Right, so one more time. Initially, there was no iron thiocyanate. We made this by mixing together solutions of the iron 3 and the thiocyanate. So we had this concentration of each of these ions to start out with. This was 0. There wasn't any of this initially. Alright, so the next line is to change. Since we're not starting out with any of this is formed at the expense of these two. So this goes up and these two go down. Well, how do we figure out how much we had of this from the graph, right? We measure the absorbance, we consult the graph we made this week, we figure out the concentration. This is how much this goes up, and these two go down by the same amount. So if you start with 0 and you add 4.25 to the minus fifth, you can finish with 4.25 to the minus fifth. So we add it here, and in this case, we subtract, and that gives you these equilibrium concentrations, and you go and plug them in. And that concludes this video.